Okay, hello everybody in my Physical Science 201. Now this is a video made for the purpose for online learning of a physical science at home, and this video will last about 30 minutes and with a very small size, and you are able to view it over and over again as long as you have an iPhone or access for internet at home. So it will serve the purpose for you to watch it, learn it, repeat it, and review it to understand the concept with a longer retention time. Alright, this is of course for Physical Science SCI 201, all sessions. Now since it's only 30 minutes, so that considered as part 1. Alright. In the past, before spring break, we already reached the end of chapter 2, which are the two very lengthy chapters, the chapter 1 and chapter 2, and only a few concepts left over. Those were the work and the power and the momentum. That's what we're going to try to do this on this video. If we can finish all three with all these examples explained, and according to the pre-test, you all have the hard copy are distributed in class as back-off review material. You can study at ease at home as well. So let's start it on whatever left over before the spring break. So let's get into work. What is work? Work means the object was under the force and being moved for a certain distance, then that work is done to the object. Now, so that tells us work should be expressed as the mass multiply the acceleration, which means the force, and then multiply the distance, it travels, right? Now it's simplified into m multiply a multiply d, which stands for an English term called mad. And that's what I said in the class a couple times. That's why nobody willing to work, because work makes everybody mad. Alright, remember that. But this expression for work actually released the giveaway, the unit for work. What is the unit for work? The mass unit in international system is going to be a kilogram. And the multiply acceleration, right? Acceleration has a unit for meter, the length over time being squared. So multiplied meter, which is here is printed, m stands for meter, and s stands for seconds. But then you move the object for a certain distance, which also in the term of the units as meter. So you multiply meter again. Now that gives a unit. We can combine them into kilogram, meter squared over second being squared. Alright, now this also has a scientist's name was honored into. It's called Joule. Now another way to remember this is if the mass multiply the acceleration by the Newton's second law, that's the expression for the force. And then also after Newton's name as Newton as unit for force. So this can be also written into Newton meter. So that is the unit for work. Then after we talk to work, if you think you're sick and not able to go to work because you're so sick, so weak, so you don't have energy to work, right? So what is the energy defined? So the energy defined, energy defined as the capacity to do work. And it indicates work and energy seem to be related. And also we are able to say they are almost equivalent. So in that sense, the energy would have a unit as the same as the unit that of work. So that is the unit for work, joule, as well as for energy. Right? We already talked about this. Now, we already did that before spring break. Now, what left over is, if you try to do some work to some object, so you have to either move it, apply the force over it, and at the same direction of your force application, and then move the object for a certain distance, either horizontally or vertically, right? With a certain, acceleration involved in the force, and then move a certain distance. Then that's the work done, right? If the work done by you are a man, and then you have limited power, and it take a long time. But if you have machinery to do the work for you, take short time, that gives you the efficiency of the work done between you and the machine, right? So that indicates something. We are able to describe this kind of situation we call power. So what is power? Power is actually the effectiveness of the work being done. So let's introduce the concept called power. Alright, power in terms of P, right? And the power, if we have this example, right? Power is the effectiveness to do work in unit time. Now, what is the unit time? In other words, if you take 30 minutes to finish the job, but the machine only takes 2 minutes, then that's about 15 times faster than you. That's the power, so that you are able to state that machinery, the forklift, for instance, is 15 times more powerful than my manpower, right? So this is going to be expressed with formula power equal work over time. Then the units should be what? Work units joule, right? Joule over seconds, and then joule over seconds you can open up is going to be kilogram meter squared over second being squared, and then this will be divided by right here by seconds again. So that gives you final in SI system the kilogram multiplied meter being squared over second be what? Being cubed, right? Now this also has a name attached to it. It's called watts. It's an English scientist. His name was used to honor him. This unit being used to honor him, called watts. Now, if you never heard of watts, I'll tell you where to look. If you still have the old light bulb, right? Light bulb, and then you look at the glass on top of the light bulb, it says 40 watts, 40 W. All right, the simple term is W. W. All right. All right. So after we introduce that, we want to have a little discussion. What's the difference between all those units, right? From the beginning, we talk about work, and the kilogram, right, is the mass unit, and the meter per square second is the acceleration unit, and the meter is the length unit, right? And then, but if you have the mass multiplied acceleration, so kilogram meter per square second, that's called a Newton, is the unit for force. Then you multiply another meter, which is distance traveled for the object being moved under certain kind of force and the work done to it. And then that will be the meter squared. And then so we call joule, become a new unit. But that is basically Newton multiplied meter. So the Newton meter is under units. Now here, if we try to look at, to understand this unit for power, it just have a unit for time underneath as the denominator. So there is the unit conversion, as you, for example, right? The units of relations. Let's put relations, right? Relationships, right? Between force, work, and power is as from kilogram meter per square seconds, right? That's the force, that force, right? Then the work equal force multiply distance equal here force, and also we call it Newton, right? So we put here Newton, that's Newton. So force equal Newton or kilogram meter over the second squared, and then multiply the meter again, the D outside, that's a force right here. So that give you Newton meter, right? Then this is the force, this is work. Then the power equal, right? Power equal the work over time, right? So you have the work is kilogram meter square over second square, right? And then you divide by meter, divide by second again. Then you have a watts. Right, watts. So this actually is cubed because you move up as denominator combined with square of seconds, right? The relationship. Now there's one problem in the pretest. We specifically made this problem for you to understand the sequence of those units, their relationship in between, and you are able to recognize them and then distinguish them. So there's one problem. Let me see, what is that problem in the pretest? Either 20, 25 or 26, let me see. Well, you may find out, I don't know exactly where is the number for that particular problem. Could it be earlier? Showed up in the early portion of this pretest. Alright, so let's do one example. Right? So if you have, let's use one of those problems in the pretest, right, to explain to you so that you are able to work them out afterwards. Say number 26, all right, pretest. number 26. Number 26 says, a nurse pushes a 75 kilogram patient. So the mass is given, right? The mass is given equal 75 kilogram. Right? And on a 15 kilogram gurney with an acceleration at 0.6 meter per square second for a distance of 2.5 meters. How much work does the nurse produce? Now here is a small trick right here. What's the mass? The mass for the man is 75, right? And you have to add the mass and the man, right? The gurney, and then the mass for the gurney is 15 kilogram. So the mass total is going to be 75 plus 15. That would be 90 kilogram. Now, from the problem, the acceleration the nurse pushed the gurney is given as 0.6, I think 0.6 meter per square second. And the distance traveled is 2.5 meter. Now that's meter right here, right? Printed meter. It's not non-printed, it means mass, right? Let me put it here, that's mass, right? That's mass right here. Alright, that's mass. Now, so the work done by the nurse equals the mass pushed by nurse, the total, right? The mass total, and multiply the acceleration of the object moved by the nurse, and then multiply the distance, right? So it should be 90. If you put a kilogram down there, that's fine. If you don't, you know the end of this problem, the solution should have a unit fitting to the work, which is what? Joule, right? So multiply, if you use a parenthesis, multiply acceleration 0.6 meter per second square, and then multiply 2.5 meter. That gives you, use your calculator, you know, and let's say it's 54 Newton. This is 54 Newton, 54 Newton, and then time 2.5 meter. That will be 135 joule. Now, by the way, remind you again, joule is the initial of scientist Joule, right? His name, after his name. After him, and then J is capitalized. The capitalized in this particular case, capitalized, just like a watts. W is capitalized as well. Newton's capitalized, and except the one we already mentioned in the past. Another units used for energy is called a calorie, right? And a calorie we already introduced the calorie, and the 1 calorie is 4.184 times bigger than the joule. But that calorie, the C is not capitalized. It is italic. And then if you see the calorie, the C is capitalized on food label. That means a value of capitalized calorie is 1,000 times bigger than this lowercase c, small calorie. So that is the difference here. We're going to reach that point in the near future. Okay, so I think you all have the clear view for these notes. Now I need a space, so I need to erase them from top, all right, to continue, all right. So let's see if we are able to get into the power, right? Concept, give some example to learn how to learn concept of power to solve problem. Alright. Let's see if we have anything given in the pretest. Maybe there, maybe not. Right? If not, we are able to make one. Let's just make one. Alright, let's just make one. Example for power. Alright. So let's see. A man, right? A man lifts a box of 40 books, weighted, let's say not use weighted book. Let's just put books of 5, let's say 5 kilograms each. From a box from the ground. From the ground with let's say 200 Newton force. Right? Now let's say in 3 seconds. Alright, 3 seconds. Alright, and to the desktop $1 meter above ground. Right, that's the distance travel from ground. Lift 40 books, 5 kilograms each. All right. Now, question asked: what is the work done by a man to the box? To the books. Let's say to the books, because the box, right? To the books. And what is the power the man generates in the action, in this work? Let's see if we are able to figure it out. That's just made up my head, okay? Alright, so as I said in the past, if you want to solve a problem, the best way is read a statement and collect all these known given quantity into a list, and then try to try to find a suitable equation for solving the problem of the unknowns, right? And then we are able to figure out if there is conversion involved, unit conversion involved or not. And then we try to convert all units into SI system first, and then simplify the equation, then plug all these known quantity into the simplified equation, then solve the problem one shot. Much easy, not complicated. So the answer or the solution, right? Answer. So the list of knowns, right? Now, if we involve some work done, work is expressed as MAD, MAD, the mass, acceleration, and the distance, right? In this case, it seems to be the mass given, right? The list of the mass. The mass total, right? Mass total for the books. So mass total for the book is 40 books right here. The 40, right, books, and multiply 5 kilo per book, correct? That gives us, what, 200 kilogram. Oh my God, it's very heavy. 200 kilograms, about 400 some pounds. Now this man needs a machine. It's not easy for him, but let's say his Superman can lift 400 pounds, all right? 400 pounds, that's number one, unknown value. And then it doesn't give us the acceleration, but it does give the force this man can produce. I don't know if this number fit or not, but we just picked up this 200. So the force equals 200 Newton. 200 Newton. Right? The 200 Newton actually has what? Has the acceleration inside, but we don't know. But anyway, so then the distance traveled is the 1 meter. Right? Then the time duration 3 seconds. 3 seconds. See if we are able to figure it out. So the answer for the work, right? Equal W equal M A D, or we can say MA is force, so force times the distance. So in other words, we don't have the value for acceleration. We do have the mass though, but we don't have the acceleration. We're given the force, so we skip that part. We have the force. We can directly reach the amount of work from the force. So the force is going to be what? 200 Newton. 200 Newton is what? 200 Newton is 200 kilogram meter square over second square. And time, oh, that's the force, right? And time, the distance is 1 meter, right? 1 meter, right? So what happens? The work done by the man is 200 joules, right? 200 joules. That's 200 kilogram meter square over second square, and that is joule, right? 200 joules. All right. And then what is power? The power the man can generate. That's not too big, but let's see what it is. So here's the what? Work over time, right? The work we already found out is 200, and times what? Times 3 seconds, right? Times 3 seconds. Times 3 seconds, and so the work is 200 kilogram meter square over second square, right? But then you've done this much of work in 3 seconds, so you divide by 3 seconds, right? Is that right? 3 seconds time, right? 3 seconds times 3 seconds. Now you have this going on top of, so you have what? You have 200, right? Kilogram meter square over second square, but you multiply the 3 seconds move on top. If you still confuse that, try to recall we already explained in the past how those fraction or complex fraction works out simplified in those cases. So it should be the 3 seconds moved up. Let's see if I use another color pen, right? Let's move up. So be side by side as the denominator to combine with the 3. You cannot forget the 3. The 3 seconds should stay there. So then the second times second square become